This is an introduction to Docker that I've put together as a slide deck and some terminal examples for the interns first and foremost, but for those in the company who want to know a bit more about Docker, because they're not familiar with it, or kind of how it works a bit under the hood, you might find this useful also. Okay, so like historical context, I guess, what Docker is and why it made such an impact when it came along, because I think it's important to appreciating why it's why this whole container movement and Kubernetes and all that has kind of taken off so much. Okay, so if we make a comparison to how software deployment was before Docker, where we might build our application and put it into an archive like a tar.gz or a zip file or something like that, and some installation scripts to go with it, and we distribute it in that way. So we're going to use that as admittedly a bit of a straw man argument, but because it's educational on what's important about Docker and what it brings. So when an application runs, it has its application code and binaries and all that, and its config and data, of course, but it has other dependencies that it requires in order to run, or it might require in order to run. So if it's a Node application, then it requires a Node runtime, a Java application, the JVM, and so on. Depending on what the application is doing, it might have some tools in the operating system on which it depends. It might call out to, I don't know, cron, or it might need certain certificates to be trusted installed into the OS. It might need to use, I don't know, curl, whatever commands that are on our system. It might interact with dbus and the like. At a lower level, there are also system libraries. So if our application is a compiled binary, let's say, like C or something written in C. It doesn't have to be written in C for this to apply, but let's say your application binary is generally dynamically linked, meaning it's your application code only, and the common Linux components like libc and libssl and various other things that it requires, that it expects to be there, they don't get linked into the executable, into the binary. They're just assumed to exist on the operating system. So when Linux runs your process, it is actually running your process and dynamically linking it in with other things that it needs, such as libc, the standard C library. And this is something that's happening under the scenes whenever you run any application on Linux. Now, and these system libraries are they're generally the files that end in .so, and they might live in a directory like userlib, something like that on Linux. And we have equivalents on other operating systems, like in Windows. These are DLLs, I guess. We might have some more subtle dependencies as well that are not files, but maybe some configuration. An application might need to open a lot of files, deal with a lot of files, and therefore if a given host has ulimits open file handle settings, set in such a way that an application is only allowed to open a handful of file handles at once, then the application is not going to work. Ulimits is a tool that system administrators will use to protect against certain kinds of attacks, say fork bombs and runaway processes and that kind of thing. It's a common thing to be configured differently on different hosts. And as you move your application from your laptop through to like dev to staging and production, if you're deploying in this manner with an archive and some scripts, then you will find differences between hosts. And that will be, and they may impact the functionality of your application, i.e. it may not work. And these differences between hosts are not due to the carelessness of a system administrator necessarily. Like in an organization, you might like ours, where we have dev, staging, production servers. You might also have performance testing environments. It's natural for them to be configured differently because of their different usage profiles. You might also use different distributions across the organization for different purposes in different departments and that kind of thing. It happens. It's not so strange as it sounds. So we have a portability issue where we unzip our archive on a different server on a different host, and we run it and it doesn't work because of differences in dependencies, be they configuration or files or tools. Generally, we deal with this by running each application in its own virtual machine, in its own VM. That very neatly deals with this issue. It also deals with the issue where we might have multiple conflicting dependencies between applications. So you might have two Java applications that want to run on the same host, but they use different versions of the JVM. That is doable in Linux. Likewise, different versions of system libraries, but it's a bit of a pain. And if we can avoid this, it makes our lives much easier. All right, so what is Docker's solution to this problem? It is the complete encapsulation of dependencies. When you distribute an application as a Docker image, it is not only its application code and config and data, it is also the application runtime, be it Node or Java or whatever, various system tools that it might need, probably loads more that it doesn't need in many cases, and OS libraries. Generally, you would distribute it with effectively a Linux distribution and associated tooling with it. Not the kernel, however. We'll come back to that later. All that is needed to run a Docker container on a host is the Docker daemon and a Linux kernel, in more or less. So this solves the issue of conflicting dependency issues and portability by Docker does this by encapsulation of dependencies. Okay, issue number 2, why software deployment was hard in this world we describe, in a pre-Docker world. If we assume that we've taken the lessons of the previous slide and we want to distribute our applications with all of our dependencies encapsulated, then we have a problem where we have a kind of waste of space kind of problem, an inefficient use of storage and bandwidth. This is because, say, take app 1 and app 2 here in this diagram. They both built on Debian. They both use the Node runtime. I'm suggesting here that they're using the same version of the Node runtime. The only thing that differs, hence the colors, is the application code itself. So if we were to package up that whole vertical stack of app 1, Debian and the Node runtime, and app 2, this is at least tens of meg, possibly hundreds of meg. Where only a few megabytes, if that, are going to vary from between app 1 and app 2. So if you are on a host and you wanted to download app 1 and app 2 using this method, you got 2 massive downloads, most of which is duplicated. So not an efficient use of storage and network, and costly for that reason. Now, Docker solves this by using a layered file system for images. A Docker image is not simply a tar.gz or a zip file. You can think of it as a layered stack of such archives and some metadata describing how to run it. And it is smart enough to know that for app 1 and app 2, those Node runtime layers or the Debian layers are the same, and it doesn't need to download it twice. In fact, it doesn't even need to store it twice on disk at runtime through copy on write file systems, but that's a bit out of scope of this here. So given this, as an exercise for the listener, how many unique layers must be downloaded to run all 4 applications here depicted on one host? Okay. So issue number 3, isolation. So let's imagine, just in order to explain this, let's imagine that we're going to co-locate 2 applications on the same host. So 2 applications, we want to run them on the same host. And we're going to talk through various scenarios of that to explore some of the security implications. So firstly, we imagine we have 2 applications that are built in-house for our product, built by 2 development teams that sit side by side and know each other and trust each other, and no reason to believe that they're writing malicious code. do we care that one application living on the same running on one host can access the files of the other application running on the same host? At least in terms of what I've described there, no, we probably don't. We'll come back to some reasons why we might in a moment, but surface level, no. Likewise, those two applications, co-located as they are, will also be able to access each other's network traffic. They'll be able to use something like TCP dump or sort of programming library versions of it to packet capture from the same network interface and read each other's network traffic. Again, do we care? This application written by other developers in the same organization that we know and trust? Probably not, at least not for the reasons we think. Now, imagine a situation where one of those applications is a REST API. It doesn't do much, just handles some incoming connections, fetches some resource and sends it back. It's not very taxing on the system. And the other one is a video transcoding application. So heavy number crunching, mathematical work, CPU bound. What issues might we see? Can you think of any issues we might find in co-locating those two applications with very different performance profiles? I guess we can imagine a situation where the CPU work of the video transcoding application is it's so busy, it's using the CPU so much that the REST API isn't able to get time on the CPU to serve its requests. Even though the work that the API would need to do is very minimal, it can't get on the CPU. So we have a noisy neighbor problem, potentially. You can imagine an analogous issue with memory usage or network traffic usage for applications. A noisy neighbor for co-locating applications on the same hosts. All right, so let's imagine a different scenario where instead of two trusted applications built for by the same organization that were co-located, we're instead a platform as a service company running our customers' applications for them so that their customers can use their applications, right? So we're something like Heroku or that kind of thing. How would we feel then about co-locating those two applications? So let's say one of them is a web application for a media company that's built just a basic static business card website for someone, and they've got it running up on our platform as a service. Are they going to care that we have chosen to co-locate their simple application on the same host as, say, some banking software? Chances are they may not understand the security implications of that. They may not care. They might think, it's banking software, it's not malicious. Who knows? They might or might not. I would argue that they should. What do you think how do you think the bank will feel about that? I think you can be quite sure that would be a sure route to losing that banking customer. They would not like that for a few reasons that we're going to explore here on this slide. Another reason with another issue with co-locating applications is sharing of, say, network resources, not just for the privacy aspect, but let's say some application wants to bind to port 80 and so does the other one. They can't both bind to port 80. We could have some other more obvious issues like that I forgot to mention. Generally, we address these issues by putting our applications in virtual machines, just as we did in the previous, as I said in the previous slide. It gives us the isolation between components that we're looking for, but at cost of quite an inefficient use of the underlying hardware resources on which we're running. Okay, so to this diagram now. Let's just talk a bit about Docker solution and then we'll come back to that. So Docker leverages two Linux container technologies in order to address these issues, that issue of the noisy neighbor and the issue of the resource isolation. They are C groups or control groups and namespaces. C groups address the noisy neighbor problem by allowing us to limit the amount of CPU and memory that an application can use. So the video transcoding software application can be capped to use like 50% of the CPU or 80% or whatever it is we might decide. And this is implemented at the kernel level. C groups are a Linux kernel feature. When it's doing its multitasking, process management, deciding which processes in the system get time on the CPU, juggling user space things with system components and all that kind of thing. It makes one of the kernel's jobs is to make these decisions. C group configuration for an application allows it to cap that. It can't be circumvented. It's at the kernel level. The other one, as I said, is namespaces, and that's for resource isolation. Namespaces address the resource isolation at a kernel level as well, and they come in several types. So we have network namespaces, which effectively means that each application thinks that it has its own network interface. So if it were to sniff the traffic on that interface, it would find only its own. If it were to look at like what IPs are available, it's only its own. It thinks it's like localhost is all it's got effectively. So therefore it can't see the network traffic of other processes on the system. And it's implemented the kernel namespace, the kernel level, when the application is like making networking requests to the kernel to open connections and whatnot. It has this blinkered kind of isolated view of the system that the kernel kind of gives it a false answer, I guess, and therefore its access is limited. We also have mount namespaces. These are kind of like a chroot, if you've heard of that, CHROOT. It means that each application thinks that it has its own file system. If the application were to do ls/ or like dir/ like to look at all the files that are on the system, it can't see anything other than its own files. We'll see what that might look like in a moment. So this addresses the issue of applications not being able to see each other's files when they're co-located. Mount namespaces help with that. Network namespaces helps with the network issue. We also have PID namespaces. PID is process ID. So when you do PS on your system and you list all your processes, they'll have an ID. A PID namespace gives your application again a kind of blinkered view of the processes on the system. More clearly, it makes an application think that it is PID1. It is the only process on the system. If it spawns child processes, it will know about those, but it can't see any others. Not even like system components or the init system or anything like that. Okay, so let's look at a few examples of this at work. So I'm going to run here an Nginx container. I'm going to call it Nginx, and I'm going to launch the process bash inside it. So this will give me a bash shell. I need to install some things for this to work. So this Nginx container quite wisely has not included a bunch of system tools that shouldn't be needed to run Nginx. So bear with me for a moment while I install them. I'm just installing curl and netstat and ps. So you would have noticed a moment ago when I said ps, it said command not found. Okay, ps. So we have there listing all the processes. PID1 here is bash, the process we're running here. We're at the terminal. I also launched PS, so that when I ran PS, I saw PS2, therefore PS also, therefore that appears too. So I'm root, so I'm effectively I'm looking at all processes as far as that container is able to tell. It's asking the kernel as root, give me all the processes on the system, and that's what it sees. That is PID, thinks it's PID1. That is PID namespaces at work. So let's, down here in the bottom terminal, I'm here on my laptop rather than inside the container. I'm in my home directory there. Let's ask this system for all the processes. We're going to see all kinds of things, browser and Zoom and Slack and various things I have running. But here we see the bash shell where I launched the Docker container. but that's not our container itself. Up here, we see the Docker daemon. It is running a bunch of containers that are not relevant to us here, because I also have Kubernetes running. Down the bottom, Nginx. No, not Nginx, because I haven't run it yet. So let's me run Nginx up the top here. Oops. So let's run that again and scroll up to look for. Here we go. So we have containerd shim. Don't worry about that. We have our bash shell, which is what I'm in above here, and then I launched Nginx underneath that, and it has a master and a worker process. So we can see here that these processes have process IDs in the million range. Million? Yes. Whereas from the view within the process, within the container, within the PID namespace, it thinks they're PID1 and PID3162. Okay, so that is PID namespaces at work. Now, inside the container here, we can do netstat to list all the open ports, and we can see here that we have Nginx bound on port 80. So we should be able to do this from within the container, and we can see the Nginx homepage. Cool, right? So if we jump down here onto the laptop itself, outside of the container, that's not going to work, right? Why not? We can see all the ports that are bound on my system. There is nothing on port 80. There's only one thing that looks vaguely Docker-ish, and that is the Docker daemon itself. That's not what we're looking for. So how is it that I have a port bound inside a container and I can't see it from my host? That is because the container is running in a network namespace that has its own isolated view of networking. Now, it's not entirely removed from the host. Like if I, on the host, do ipadder, which is like, ifconfig, where we list all the network interfaces, and we see that we have loopback, things like this, and we look, I haven't got that installed inside the container, and I don't remember what the, let's try IP, I think it might be something like that. No, never mind. But all we would see there, if we run it, is just something that looks like this. We would see loopback. It only has localhost as far as the container can see. Now, on my host here, we can see we have loopback, we have my unused Ethernet, we have my Wi-Fi, but we also have we have the Docker daemon created bridge, and a bunch of these other things starting with either BR or VETH, virtual Ethernet. These have MAC addresses. They have IP addresses in many cases. So Docker is doing some magical network plumbing, let's call it, for the purposes of this introductory lesson, I guess. It's doing some network plumbing magic to make this work. Let's see what it's doing. Well, let's learn a bit more about what it's doing. If we on the host do docker container inspect Nginx with our host name, with our container name Nginx, we can see this network settings block, and we can see that container has an IP address. We can fetch that IP address and curl it and access Nginx, and we see our logs appear up the top. So this is just regular Linux networking plumbed together using IP tables and network interfaces by Docker and hidden from you entirely. I show it to you because I would just want to demonstrate that this is the isolation primitives of namespaces at work. Demonstrating C groups is a little more difficult. We'd have to sort of like maximize the CPU and see that it gets throttled, but you'll have to trust me on that one. Okay, so coming back to this diagram now, we have different kind of isolation on the left here with containers, or Docker at least, and on the right here with VMs. a few big differences you'll notice when you compare them. One is that on the left we have the Docker daemon, on the right we don't. The other is that on the right we have the hypervisor, on the left we don't. But also this one here. Each application has its own guest kernel and operating system. Whereas on the left we have the host operating system. So here on my laptop I have Arch Linux running, so the Linux kernel and all the stuff that Arch bundles with it. That's that layer. Then I've got the Docker daemon, and I've got my processes running as containers, application processes running as containers there. Whereas on the right, each of those VMs, so we're imagining this is the case like if you launch VirtualBox on your machine to run Linux within Mac, or indeed if you just run Docker all on your Mac because that runs in a VM, or say an EC2 instance running on whatever behemoth machines Amazon use. That's the picture we're looking at on the right. We have an entire copy of our operating system for each host. Now the isolation that the hypervisor gives us is effectively complete for our purposes. It's not brand new technology, it's solid. It's not full of bugs where you can access the information of your other hosts, right? This is solid stuff. But that isolation comes at a huge cost in terms of resource utilization of the underlying hardware. Another thing to consider, we'll come back to a bit later, is the fact that all applications here on the left are sharing the same kernel, whereas all the applications on the right have their own kernel, and they don't share this host kernel. This has some security implications that you might want to think about. We'll come back to them in a moment, or indeed very shortly. Okay, so having gone through all that, how Docker addresses this, these issues of portability, the storage and networking costs, and the isolation, we can have a better view of what are containers and what is Docker. You may have heard the phrase Docker containers are lightweight VMs, but as we've just seen, containers are just processes, right? I was able to list them with PS. We could see Nginx running there. It's just a process. It's a process that has been configured with some isolation using C groups and namespaces, some kernel features within Linux. And that isolation is a trade-off. It's quite a big trade-off. So when you compare to what you get with the hypervisor and VMs, which is complete isolation, with containers we share a kernel. I asked you to think about what might be the security implications of sharing a kernel between containers on the same host. Some of the things you might have occurred to you is things like, say, buffer overrun attacks. If you have a vulnerability in an application that allows a user or attacker to peek beyond the end of an array into another part of memory, you could, in theory, without further mitigation, be accessing parts of memory that belong to other applications. And what kind of things might we have in memory in applications that we don't want a malicious user to be rummaging about and finding? Things like AWS access keys, database passwords, all the kind of secrets that we'll use in our applications that we want to keep secret. They can be compromised, as well as private data, customer data, that kind of thing. Also, another thing to think about is kernel exploits. A kernel is a piece of software like any other. It has bugs. It has had bugs throughout history. They get found and patched all the time. It's a reason to keep your systems up to date. But not every server and every administrator is rigorous about updating their kernels, so we might have old kernels out there with known vulnerabilities that attackers are going to be looking for and wanting to exploit. A famous one is Dirty Cow, copy on write bug, which allowed you to escape the isolation primitives afforded you by namespaces. If your kernel is vulnerable to, if your kernel has vulnerabilities, all of your containers on your hosts it can be compromised, depending on what the vulnerability is. So we're not protected from kernel exploits, whereas in the VM world, the guest kernel is what gets compromised, and then you don't get access to the other VMs. So our isolation is not quite so complete, not nearly as complete as with VMs. It's compromised. Another thing to consider is privileged containers. So you can run containers with Docker where you turn off certain security features. You give it extra elevated privileges because maybe the container you're running needs it. You can tell it to use the host networking rather than the network namespace. A lax administrator that allows users to create applications in containers that with these kind of security flaws opens themselves to compromise of the host. Giving someone access to a privileged container is effectively give them the root access on the host. In fact, it's worse because that user never logged in and there's no audit trail for what that user did. So it is very important to keep that in mind. So given we've learned about containerization technologies and what are containers, i.e. their processes, what is Docker? So Docker is not, the invention of Docker is not, doesn't coincide with the invention of containers. Container technology existed long before it. Docker, before being called Docker, were called .cloud. They were a platform as a service company doing something like Heroku. The container technology was already around, and a number of companies like .cloud and Heroku were exploring container technology, as of course were Google. They were committing container technologies to the Linux kernel early on. But after it had been out there for a few years, companies like these began to write tooling around it, and Docker is kind of the result of that. It is .cloud's efforts to make easy to use containers, make containers easy to use. They've done that by building a Docker daemon which supervises and runs containers. So it launches containers, but it also supervises them. We saw that Docker-D was the parent process of our containers when we were looking at them in PS earlier. Docker is also an image format for the efficient storage and distribution of applications. This is what we were talking about on the earlier slide, where different applications will share lower layers. Docker images, layered image format is what allows for that. It's also some networking magic to connect containers together and expose ports, and giving each container its own network interface, an IP address, and all that kind of thing. It is also some security features to lock down what processes can do. A container running as root can't do all the things that a regular process running as root can do, not because they're special and not just and not simply containers, but because Docker wisely limit what containers are able to do, limit a bunch of system calls that they're able to do. And perhaps first and foremost, it is an excellent user interface to otherwise hard to use low-level Linux functionality, and as a result they've revolutionized how we build, ship and deploy software. Okay, so having covered those basics, if you want to have a play with putting some of that knowledge into practice, on Katacoda there are some free introductory Docker exercises, and you can go and play with them in a browser without even having to install it, or find any number of other tutorials out there on the internet. I want to do a couple more of these, maybe another Docker one, and then do some Kubernetes ones, because I think people will find them useful.